telling you about orthogonal calculus before I tell you about localizations of it. And then at the end, we'll give some kind of easy applications. And by this, I mean applications that don't require me to be able to compute anything. So let's get started with the actual calculus. And of course, if there are any questions, it is always best to just shout them out. So orthogonal calculus really comes from some geometric problems. So we want to study functors and that go from some category of vector spaces, let's just say over the real numbers, to base spaces, or maybe spectra if you are so inclined. And all the examples are kind of geometric. So the standard ones people care about are if you have, let's say, a manifold M, a smooth manifold. You can think of a functor which sends a real vector space to embeddings of your manifold M into this, plus or minus some technical details. So if your manifold M here was the real line, this would be like a space of long knots. Or you could do something else. So that's one example. You could have the functor be top, which sends some vector space to the classifying space of the group of homeomorphisms on OR-K. So this is kind of an odd thing to choose, but in some sense, this is related to the classifying space of diffeomorphisms of disks via some smoothing theory. So study one, if not the other. And the calculus is constructed in such a way that it uses homotopy theory to try and understand these geometric objects. And it is completely analogous to differential calculus from undergrad. So the analogy goes as this. So from undergrad life, we have some function on the real lines, and we're saying we're replacing this with a functor from vector spaces to spaces. And to this, the thing you do, you build a bunch of polynomial approximations to this. And you know that the limit of these guys is f. So we try and do the same trick here. We build a bunch of functors, find in the same category.
So I don't see the bottom of the page.
Oh. Is it better if I move it up? Fine, I can move over. So to this functor from vector spaces, let's call it f. We build a bunch of approximations to f on the same category that are supposed to act like Taylor polynomials from differential calculus. So the analog of Taylor series is then a Taylor tire. And since orthogonal calculus was first invented by Michael Weiss, sometimes it's called a Weiss tire, depending on what you read. And it is all sitting under f, and there are maps from the first approximation to the 0th, and from the nth approximation to the n minus first, again under f. So the goal really is to try and use this tower of approximations to understand the homotopy type of f. And a kind of standard way to use a tower of something to understand the homotopy type of something else is look at the difference between the terms in the tower. So if you want, you're looking at like an associated gradient of a filtration. So you can take the homotopy fiber of each horizontal map, gives you a new functor. And we can use these functors, these DNFs, to try and understand the homotopy type of F via the following spectral sequence. So it's a bicycle can spectral sequence, whose E1 page is the homotopy groups of these layers. And it converges or attempts to converge to the homotopy groups of the limit of the approximations. So if your functor is particularly nice, and by this I mean that the entire converges, the map from the functor to the limit on some vector spaces and equivalents, and then the spectral sequence attempts to converge to the homotopy type of F, maybe at B. Okay, so we have a spectral sequence starting off with these guys, hopefully ending up here. So the kind of obvious question is, well, can we actually calculate these guys? And to do that, you should think of these guys as, in some sense, so this DNF is the homotopy fiber of the map from the nth approximation to the n minus first. So it's really a version of the difference between little pn of x and pn minus 1 of x from differential calculus, right? And we know what this guy is. This is the antiderivative, well, maybe at 0 if I cheat a little. So really what you want is a formula for this guy involving some notion of the derivative of a functor. And that's exactly what we're going to do. So let's talk about derivatives. Okay, so let me just, again, say I'm working with a functor from vector spaces to spaces. Let me give you the definition of the nth derivative and then kind of tell you why this is something you might care about. So if you have some functor f, then the nth derivative is given by a homotopy fiber sequence so it is the homotopy fiber of a map from f on some vector space V into the homotopy limit over the non-zero subspaces of or n, the value at f on these guys. So this looks like a little bit of a weird definition, but all it's really saying is that if you take your functor f, evaluate it in some vector space, and then restrict it to the poset of subspaces of Rn, you get a functor that looks something like this. And the nth derivative is, I guess at V, is the total fiber of this guy. So if you think about cubical homotopy theory, this is something that takes a functor from the poset of subsets of n elements to some category. And you can talk about total fibers, cofibers, and so on. All we're saying here is that we kind of generalize this, so we can talk about functors from the poset of subspaces of Rn. And you can generalize much of cubical homotopy theory to this Rn cubical world. And you can talk about total fibers, total cofibers, etc. And we're defining the nth derivative to be just the total fiber of some big cube. But one thing to note about this cube is that you really have to take the topology into account now. This poset of subspaces of Rn is topological. So by this, I mean it has a space of objects and a space of morphisms. Those internal category spaces. And when you're doing these constructions, you have to take this structure into account. This is easy to see on a smallest example. So if you take, let's say n is 2, then suppose that you have one copy of R0 sitting inside R2. You have the one copy of R2 sitting inside R2. You can fix a copy of R1 sitting inside R2 by choosing the x-axis in the plane. Then you have all rotations of this about the origin. So the poset starts looking something like this. So in particular, the space of objects is just a disjoint union of Grassmannian manifolds, and the space of morphisms is just a disjoint union of flags of subspaces. And this geometry is actually kind of useful. So this geometry would be linear algebra if you want. It gives this nth derivative more structure. Namely, there are maps that go from the n-fold suspension of the nth derivative on some vector space to the nth derivative on that vector space plus a copy of the real line. So this is, in some sense, saying that this nth derivative is a spectrum, but of multiplicity n. So if you want another way to say this, on the category of functors from vector spaces to spaces, there's a functor called NS, which sends a vector space to the one-point compactification of n copies of your vector space. And this is a commutative monoid in this category of functors. And then the nth derivative is just a module over this guy. So you have commutative monoids as rings, and then you're talking about module over a ring. But this is also good because this gives us a clean way to get a spectrum out of this guy. There's a change of rings adjunction. It's really change of commutative monoids from modules over this guy NS to modules over it when n is 1. This is just a model for spectra. And so you can send the nth derivative here to get a spectrum. And this ends up being a spectrum that actually is acted on by the orthogonal group. And when people talk about derivatives, what they really mean is this spectrum together with this ON action. And this might, in some sense, seem like, okay, you can do this, but is it actually something you can calculate? And the answer tends to be, in low cases, yes. Let's look at some examples. So there's the functor, it's called BO, it sends a vector space, so really an inner product space, to the classifying space of its orthogonal group. So some low-dimensional calculations of this were done by Michael Weiss, and he showed that the first derivative of BO is the sphere spectrum. The second derivative is a desuspension of the sphere spectrum. Then it gets more complicated. Third derivative is loops 2 on the mod 3 Moore spectrum. There's actually a closed formula for these guys. So I guess this is a theorem of Gregor-Rome's. Says that the nth derivative of BO is maps from some complex called Ln to the suspension spectrum, the one-point compactification of the adjoint representation of ON. And this Ln guy, you should think of as some kind of topological version of the partition poset complex. So you take the poset of subspaces of Rn, or direct sum decompositions of Rn, that poset, and then you take the geometric realization and unreduced suspension, and that gives you this guy. So this looks like the derivatives of the identity functor from Goodwin calculus, if people are familiar. There's another example that I want to talk about a little, which is the functor B top, which sends again a vector space to the classifying space of the group of self-homeomorphisms on V. So again, we know what this is by some work with Michael Weiss. We know that the first derivative of this guy is Waldhausen's A theory of a point. So if you want rationally, this is the algebraic K theory of the integers. And we know its second derivative rationally. So this is some pretty recent work of Mano Kranich and Oscar Randall Williams. Says that the second derivative of B top rationally is maps from S1 to a desuspension of the sphere vector. But other than that, we know absolutely nothing about this functor, essentially, and we only know this, the second one rationally. So this is kind of one of the motivations as to why you'd want to think about homological localizations of functor calculus. You'd want some kind of framework in which these rational computations could be done maybe slightly more explicitly or into higher derivative levels. So let me maybe say some things about the formula then for these DNs that we have to start. Are there any questions at this point?
Did you want to mention which monoid homomorphism you were doing change of monoids with respect to?
No. It is the, where did I have it? Here. So there is a monoid map going this way. And I restrict along this here. This is this guy here. Yeah. Okay, so what do we have so far? We have some functor f on this category of vector spaces. To this, we assigned its nth derivative, and to this, we assigned some spectrum with an ON action. So the obvious question is, well, can you go in reverse? Can I start off with some spectrum and build a functor in the opposite direction? So here's one way to do this. Start off with a spectrum. I can then make this functorial kind of arbitrarily, but making a functor that sends V to the one-point compactification of n copies of V smash x. This is now a functor which lands in spectra, I guess, with an action of ON, just to keep ourselves right. I can then kill the ON action to get a functor that lands in just straight spectra. Let's say by homotopy orbits. And then I can take a loop space of this guy to get a functor that lands in spaces. And if you were to start off with these two being identical, to put in the derivatives, then this almost recovers f. It recovers f if there's two nice properties about f. So I guess this is the theorem of Michael Weiss. So if the functor f is what's called n-homogeneous, so that means that the map to its nth approximation is an equivalence, and its n minus first approximation is trivial. So think of it concentrated in polynomial degree 1. And then this loop here, this loop, comes out to give you an equivalence. So f of v is this infinite loop space, but with the derivatives. So the example is that dn of f is n-homogeneous for any n. Any n, and I guess any f. Okay, there is another way to see this equivalence. Just my slightly preferred method. So an alternative is you can look at all these adjunctions we have, right? So we have this category we started off with. Spaces. It turns out by a stroke of luck, taking the nth derivative is a right adjoint. So there's some left adjoint to this guy. And then we have our change of rings. And you can ask, well, when does this give you an equivalence of homotopy theories? And if you look inside these on the homogeneous functors, then the composite here is an equivalence of homotopy theories. So what I mean by this, to be precise, is you put a model structure in this category of functors, which represents the homotopy theory of the homogeneous functors. And then these adjunctions become zigzag clone equivalences between this homogeneous model structure and spectra with an ON action. So I should mention that this is all work of Dave Barnes and Peter Oman. We put orthogonal calculus into this model categorical framework. So we now have this formula for these layers of the tower. So we can, in theory, apply the Biesel-Kahn spectral sequence to find out something about the homotopy type of the limit. But that doesn't really tell us anything about the homotopy type of the functor we want. So we have to talk a little bit about convergence of the tower. So that's what I will do next. So very little exists in the literature about convergence of these things. But there is some kind of initial steps towards understanding it better. So we want to know when the map from f to the limit of its tower. We want to know when this is an equivalence. This map is induced by maps from the functor to its polynomial approximations. So what we could say is that if we understand these maps well enough, so by this I mean if we know the connectivity of these guys, then we should be able to decide if this is an equivalence or not. And that's exactly what the following definition makes precise. So the functor f is weakly polynomial if this map from, if for all n, the map from the functor to its polynomial approximation is, let me write down the connectivity estimate, it's n plus 1 times the dimension of the vector space up to a shift connected. So this is like linear in both n and the dimension of the vector space. And if you know this, because this is linear and goes to infinity as n goes to infinity, it tells you that this map in question will be in equivalence. So that's a fine definition, but useless for examples. So the functor BO that we had from before, again, sends a vector space to the classifying space of its orthogonal group. This guy is weakly polynomial. This first appeared as a statement in a paper of Gregoron's, later in a paper of Barnes and Eldred. I think Barnes and Eldred were the first people to have an actual published proof of this, but it's been known for a long time. Even more interestingly, if you look at the functor that sends a vector space, we call it W this time, to the space of linear isometries from some fixed V to W, then this is weakly polynomial. And you might be wondering, okay, that's a very particular functor. Why does that matter? Well, for the finite, the reason that if you know that this guy is weakly polynomial, then you know that lots of functors are weakly polynomial. So I guess one way to say it is that finite cell complexes in this category of functors to spaces are all weakly polynomial. So in particular, they all have convergent towers. So the essential reason is that finite cell complexes in this category of functors are built in finitely many steps out of things that look like linear isometries. So you can build using these guys to give you weakly polynomial guys. There's a hopeful example. Let me tell you about it. That is going to appear in some joint work with Gregoron once we flesh out the details. But if M and N are some manifolds, that probably means smooth, then you have a functor that sends a vector space to embeddings of M cross that vector space and N cross that vector space. And this should be weakly polynomial in, I guess, codimension probably at least 2. So the reason for this is that this space of linear isometries, or the space of embeddings, can be expressed in terms of linear isometries, again, and configuration spaces. And using that expression, you can figure out that both linear isometries and the configuration spaces are weakly polynomial. So you can get the whole thing is plus or minus some details checking. But moral of the story is that most functors you want to think about should fit into this framework. So are there any questions at this point? Okay. If not, let's move on and talk about some localizations. So let me be a little bit more, a little vaguer. So everything I'm going to say from now on is true in the following setup, but I'll restrict attention very quickly. So C is either the category of base spaces or spectra, and S is a set of maps in this category. So this in particular means that the left bilateral localization at S exists. Then we're going to look at functors from vector spaces for the real numbers to this localization. So the example and what I'm going to focus on is when the set of maps S is, let's say, isomorphisms induced on rational homology. In which case, LS, let me just do spaces, that's maybe slightly easier. And this is the same thing as what's called LHG. Spaces, which is spaces up to rational homotopy or rational homology. So if you think of this in terms of model structures, inside these guys, there are the fibrant objects of this model structure. And if you look at the ones which are one connected or simply connected, these are rational spaces in the sense of Quillen and Sullivan. Okay, our question now is there a calculus which lands in these localizations? So maybe before I answer the question, I should tell you why one would want this. And because this is an audience which is probably slightly more algebraic than the usual audience that listens to functor calculus talks, I want to talk about some algebraic models for functor calculus, which, full disclosure, don't exist, but are a pipe dream that I would want to exist. And this is one step in getting these things. So let's say we start off with functors from vector spaces over the reals to spaces. Well, a rational orthogonal calculus already exists. This is in some work of Dave Barnes. So you can transport this to functors from vector spaces to essentially rational spaces without the connectivity estimate. Now, if your rational spaces are pretty nice, there's nothing to say, well, can't you then look at functors from vector spaces over the reals to CDGAs over the rationals? So via Quillen by Sullivan. I mean, maybe you want to take some Lie model here instead of CDGAs, but whichever. And you can ask, does this composite somehow give you an algebraic model? So if you were to do a calculus up here and transport it down here, is it the same thing as essentially transporting it here and doing the calculus on this category? So there is some evidence as to why something like this should be true. And for the evidence, you just look at the classifications. So what I mean by this is that in the standard orthogonal calculus, homogeneous functors are classified by spectra with an action of OM. In the rational case, they end up being classified by rational spectra with an action of ON. So again, this is some work of Dave Barnes. This last guy, rational spectra with an action of ON, is the same thing as, you could say, rational ON spectra, but you have to look at free or co-free guys. So this has a model, has an algebraic model. So it is the same thing, roughly, plus or minus some details, as modules over the cohomology of BSON with rational coefficients, and then you have the torsion guys. So this is Greenlees and Shipley. So in particular, if you look at what the cohomology of BSON is, well, it depends on n. So in odd degrees, it's polynomial on Pontryagin classes. This n is 2k plus 1. Even degrees, it's polynomial on the Pontryagin classes on an Euler class. So this classification of rational spectra as modules over this cohomology ring tell you that, get this in the right order, the first derivative of some functor rationally is the same thing up to homotopy as a rational chain complex. And yes, the second one, it's the same thing up to homotopy as a rational chain complex and an action of the Euler class. And so for higher ones, you'll have, depending on the arity, you'll have either an action of Euler classes and Pontryagin classes, or an action of the Euler class, or sorry, just an action of Pontryagin classes. So on the side of classifications, we have a pretty neat algebraic model for rational spectra with an ON action. I guess the kind of pipe dream is that this can actually be made into some kind of algebraic model for the functors, or even the kind of building blocks for the calculus. So the homogeneous parts or the polynomial parts using some kind of target as CDGAs or the algebras. So then the standard thing one can do as a homotopy theorist is ask, well, what next? So if you could figure this out, then what's to stop you going to higher chromatic heights? So rationalization is height 0. And this big hierarchy of like prime ideals of stable homotopy theory, if you will. And at higher heights, we know that basically there's a version of Quillen's classification of rational spaces to higher heights. If I could spell higher. Namely, this is some work of Heights-Hoyt's. And he says that Vn local spaces, so V0 local spaces being rational, are equivalent to Lie algebras in Tn local spectra. So one could ask, is there some kind of model for a Vn local calculus, so a calculus on Vn local spaces that's built out of Hoyt's model using Lie algebras in Tn local spectra? And so having a theory of localizations of orthogonal calculus is kind of the first step in this program to try and come up with some algebraic models. Any questions? Okay, if not, let's look at some local calculus. So I'm going to restrict to a homology theory now. So I'm going to say this E star is a homology theory. So I mean that it's represented by a spectrum. So E star on some space X is the homotopy groups of X smash some spectrum E. And we're going to look at functors from vector spaces over R to E local spaces. So a model for this is a particular localization that depends on just the localization of spaces from functors from vector spaces over R to spaces. Okay, so in particular, functor f is E local if and only if each of its values is E local. And of course, you can replace top with spectra if you want everywhere. And things still remain true. So just by the actual machinery, you can crank out a tower. Maybe we give myself a little bit more space. So we have a tower. So let me draw it vertically this time. And then each of these constructions depends on the homology theory, E. So we add a little superscript E to sell this, and it also sits under your functor F. And you can, of course, just take homotopy fibers to get these layers. And now the job becomes classifying these guys. So maybe as a warning, that this E local approximation need not actually be E local. But it is in many examples. So a theorem, I guess, if I want to be generous to myself. If the localization functor is smashing, then Kn E of F is E local. So on spectra, this is saying that when I say smashing, I actually mean smashing. So this is smashing localizations. So in particular, localizations which are closed under colimits. But on spaces, I mean, smashing doesn't really make sense because you can't really smash with a local sphere. So on spaces, I just mean that it's closed under colimits. And I guess the important thing to keep in mind is the examples. So on spectra, you have the standard ones, localizations, subrings of the rationals, Johnson-Wilson E theories, complex K theory, finite localizations, etc. but I guess not things like P completion or localization at Morava K-theory. And on spaces, I guess the prototypical example is localizations at some Algebraic plane spectrum where you are a subring of the rationals. Okay, and the kind of the theorem, which doesn't use the smashing assumption anymore, is that you can build or look at homogeneous functors on this category if you want to build a model structure. And this is equivalent to spectra in E-local, in the E-localization of C with an ON action. So what does this mean? C is spaces, we get spectra in E-local spaces with an ON action. So the stabilization of E-local spaces, if C is spectra, we just get E-local spectra with an ON action. And in particular, maybe worth a remark is that if C is spaces, and we're looking at localization of the subring of the rationals, then E-local spectra is the same thing as spectra in E-local spaces. But it only seems to be true in this kind of restrictive setting. So we have 5 minutes. Let me tell you about an application of this. And an application. And this is to bicycle classes. Let's maybe remind people of bicycle classes. So if E is some spectrum, the bicycle class of E is just a set of acyclics. That's a set of spectra that tensor with E gives 0. And in particular, the bicycle class of E is equal to the bicycle class of some other spectrum E prime, if and only if their localizations are the same, or if you want they give the same homology theories. So what can we say about these in calculus? Well, we can say the following. The bicycle class of E is the bicycle class of E prime if and only if the E-local calculus is equivalent to the E prime local version. So this means that Pn E is equivalent to Pn E prime for all n. So maybe let me end with an example. So let's say I take 2 groups, G1 and G2. Let's just say they're abelian. Then we can say that G1 and G2 are of the same acyclicity type. The same acyclicity if the following 2 things hold. G1 is torsion, if and only if G2 is. And G1, well, I guess for all P, for all primes P, G1 is P divisible, if and only if G2 is. And so you can use this and the last theorem to say that if G1 and G2 are the same acyclicity, then look, the more spectrum of G1, the more spectrum of G2, I guess this is actually a result of Gauss field. So groups with the same acyclicity have Gauss field equivalent more spectra. And that's the same thing as saying that the calculus on these guys is the same. With a little toy example, since it's a group theory audience, and I guess I will stop there.
Thank you, Neil, for the talk, and for the very excellent use of the Blackboard space. Let us all unmute ourselves and give the speaker a round of applause. Okay, so if you have any questions, now is the time. You can either unmute yourself and speak, or you can put them in the chat.
Hey, Niall, it's
Hey.
me. Hey, just a question. In the setting of Goodwillie calculus, there are all these classification results of Aron and Ching about, given the derivatives of a functor, here's what you have to do to reconstruct the actual functor or the Taylor tower of it. So,
like a Tate construction type thing, right?
Yeah, usually there are two ingredients, right? There's some module structure over some operand plus some Tate data, and then
Right.
of course in the after chromatic localization, these descriptions then simplify because of the vanishing of these Tate constructions. So is there any hope of something like that in this orthogonal calculus world?
So you can, for example, you can recover, if you have a functor two spaces, you take a suspension spectrum. So you take that gives you a functor in spectra.
Mm.
You can recover the derivatives of your underlying functor, the one on spaces, from a co-bar construction on the ones on spectra.
Right.
Which I guess is the exact same thing that happens in Goodwillie calculus, right?
Right. But then to get from the derivatives to the actual functor, right? So that reconstruction problem. So that's yeah. Is there anything
one problem
like that?
One problem is easy, but the other problem I have no idea of how to do that.
Okay, but you might hope that such a problem simplifies drastically, for example, in this rational version of
right, exactly,
something, right?
It should do, yeah.
Okay, yeah, we should chat.
Sure.
Thank you for the question. Any more questions for Neil? I think I just spotted some movement in the chat. No? Yeah, I had a sort of silly question. Neil, if you go back to that theorem of yours, which had that smashing criterion.
Yes.
Yeah, here. So I'm guessing this is not a necessary criterion. Like, are there lots of examples known where this PNEF is E-local and LE is not smashing, or is that a silly question?
I think it's going to be necessary.
Okay.
Just by the construction. I mean, this PNE is a big co-limit.
Yeah, I saw that.
So,
yeah.
I mean, I think it is necessary.
Okay. So could that be, like, is that a conjecture that has already been made, or is that like an educated guess?
No, it's a true statement. So it's only
Okay.
E-local if the localization is smashing. At least on functors and spectra. Smashing on spaces doesn't actually make sense. But then you won't close under co-limits, and then it's a required condition.
Okay. Okay, thank you again. Do we have any more questions for the speaker? Let me look at the chat 1 sec.
So you mentioned the calculation of the Goodwillie derivative of top involving Walthausen's A of a point, and well, I'm sorry, the orthogonal derivative, but So in the Goodwillie situation, we do know the derivatives of 1000 of x by Goodwillie's work. Is there any sort of, is there any morphism relating the two calculuses? I mean, the Goodwillie derivative calculus and the Weiss orthogonal calculus?
So I guess one way to think about it is that the Goodwillie derivative of the identity on spaces, when evaluated on spheres, is exactly the orthogonal tower or the Weiss calculus on the functor setting a vector space to its one-point compactification. And that's a true statement if you replace the identity by any nice functor. Maybe it makes sense if I try and write that somewhere. So if you have the identity on spaces, you then get a functor from vector spaces by precomposing with that monoid. And then the Weiss derivatives of this guy without the actions underlying are the Goodwillie derivatives of the identity, ignoring the equivariance. And if you replace the identity here with some functor f, then you get that the Weiss derivatives of the composite are the restriction along this guy of the Goodwillie derivatives of your functor, if f is nice in some precise sense. So I think analytic is the required condition. If that answers your question, it may not.
Did John say something? Okay. Any more questions for Neil? All right, looks like there aren't any more questions. Thank you again, Neil, for speaking today. And
right,
let me
thanks.
thank all of you for coming here from many difficult time zones. Okay, bye-bye. There's a talk next week by, I mean, I forgot the first name of the speaker, but anyway, yeah, there's a talk next week in this series. And I hope to see some of you there. Bye-bye.
See ya.